Welcome back to the channel. Today, we're diving into one of the most extreme mysteries in the cosmos, magnetars, the most powerful magnetic objects in the universe. If you enjoy this kind of calm science documentary content, please remember to like the video, subscribe, and share it with a friend who loves space. It really helps the channel grow, and I appreciate your support a lot. Before we begin, I'm curious, what time are you watching this, and where in the world are you listening from? Let me know in the comments. Now, let's explore the strange world of magnetars. A massive star begins its life in apparent simplicity. It gathers from a cold cloud of gas and dust, slowly drawing material inward under gravity, until a dense core forms at the center. As that core grows, atoms in its interior are squeezed closer and closer together. Temperatures rise to many millions of Kelvin, and in that deep interior, hydrogen nuclei begin to fuse into helium. This process of nuclear fusion turns a small fraction of mass into energy steadily released as light and heat. From the outside, the star appears calm, a bright point, or a steady disk in the sky, but inside it is a continuous engine. In every second, countless fusion reactions occur in its core. The energy they release pushes outward, and gravity pulls inward, and for a long span of time, those two tendencies match. The star remains in balance because the pressure of the hot gas and radiation in the core exactly counters the weight of the overlying layers. As long as there is enough hydrogen in the core to fuse into helium, this balance holds, and the star shines with nearly constant brightness. For a star with a mass similar to that of the Sun, this phase lasts for billions of years. For a star with more than about 8 times the mass of the Sun, the story unfolds more quickly and ends more violently. The greater the mass, the stronger the inward pull of gravity, and the faster the star must burn through its fuel to keep itself supported. In such a star, the central hydrogen supply is used up in only a few tens of millions of years. When the hydrogen in the core is mostly exhausted and has been converted into helium, the fusion reactions that once held gravity at bay begin to weaken. The core can no longer produce enough energy to fully support the star, so it slowly contracts. As it shrinks, gravitational energy is converted into heat, raising the temperature of the core still further. Under this increased heat, a shell of hydrogen surrounding the helium-rich core becomes hot and dense enough for fusion to restart. Hydrogen now burns in a thin shell rather than throughout the whole central region. That shell burning adds extra energy, which flows outward and pushes the outer layers of the star to expand. The star swells to many times its original size and cools at the surface, taking on the appearance of a red giant, or for the most massive stars, a red supergiant. The surface cools because the energy is spread over a much larger area, even though the interior grows hotter than before. Deep inside, the helium core continues to contract and heat up. At some point, in stars with sufficient mass, the central temperature becomes high enough for helium nuclei to begin fusing into carbon and oxygen. Helium fusion provides a new internal energy source and briefly restores balance. For a time, the core is powered mainly by helium burning, while hydrogen keeps burning in a shell around it. The star continues in this way, with gravity compressing the central regions whenever a fuel supply is exhausted and new shells of fusion igniting at higher temperatures and densities. Carbon produced in the helium-burning core can fuse into heavier elements such as neon, sodium, and magnesium. Later, under still greater pressures and temperatures, those products can fuse into elements like silicon and sulfur. Each stage occurs in a nested shell around an ever denser core. The star acquires an onion-like structure with different nuclear reactions in different layers, each contributing to the overall pressure that keeps gravity from collapsing the whole structure at once. At last, after this series of stages, the core becomes dominated by iron and nearby elements. Iron has a special role in this story, for lighter nuclei fusion releases energy, because the resulting nuclei are more tightly bound than the ones that came before. For iron and heavier nuclei fusion requires an input of energy, rather than giving energy back. Once the core is mainly iron, no further ordinary fusion process can provide additional support. The star has no easy way to tap new nuclear energy. Gravity then acts almost unchecked. The iron core, unable to generate enough pressure by fusion, begins to contract rapidly. As it collapses, densities climb to values far beyond anything experienced in normal stellar matter. Inward speeds reach a significant fraction of the speed of light. Electrons are forced into protons in the atomic nuclei, forming neutrons and releasing ghostly particles called neutrinos. The collapse continues until the inner core reaches densities comparable to those of atomic nuclei. At that point, matter becomes incompressible enough that the collapse halts and rebounds, sending a shock wave outward. With the help of the enormous flood of neutrinos carrying energy from the interior, that shock wave moves through the star and tears the outer layers away in a core collapse supernova explosion. For a brief interval, the star outshines almost everything else in its host galaxy. Much of its outer mass is thrown into space in the surrounding region, with heavy elements forged in the previous burning stages and in the explosion itself. Yet the core does not vanish. Stripped of its outer layers, having spent nearly all of its nuclear fuel and compressed by gravity to astonishing density, it settles into a radically new state of matter. The result is a neutron star, a stellar remnant with mass comparable to that of the Sun, but squeezed into a sphere only a few tens of kilometers across. This compact object born in violent collapse is the starting point for one of the strangest possibilities in stellar evolution. Under the right conditions, among a small fraction of these remnants, the same collapse that formed the neutron star also amplifies magnetic fields to almost unimaginable strengths. Those rare cases become magnetars, the focus of the journey that follows, but their story begins in the quiet balancing act of an ordinary-looking, massive star. From the outside, a neutron star is small, dark, and easily overlooked against the background of its host galaxy, yet in physical terms, it is among the most extreme objects that nature can produce. It forms when the core of a massive star collapses and the supernova ejects the outer layers into space, leaving behind a remnant composed mainly of neutrons. The mass of this remnant is typically between roughly 1 and a bit to a little more than twice the mass of the Sun, but all of that material is packed into a sphere only about 20 kilometers across. This means that a neutron star is roughly the size of a large city, yet holds more matter than hundreds of thousands of planets like Earth. In such an object, the familiar structure of atoms no longer survives. Under the enormous pressure of gravity, electrons are pressed into protons forming neutrons and emitting neutrinos during the collapse. The end result is a dense fluid of neutrons with a few remaining protons and electrons embedded within it. The density of this material is extraordinary. On average, a cube of neutron star matter a centimeter on each side would weigh as much as a mountain on Earth. A single teaspoon of this matter would have a mass of around 1 billion tons. These comparisons are not meant to be dramatic. They arise directly from the calculated density of nuclear matter and the measured masses and radii of neutron stars. Gravity at the surface of a neutron star follows from this high density. Because so much mass is gathered into such a small volume, the gravitational pull at the surface is hundreds of billions of times stronger than that at the surface of Earth. If a small object were allowed to fall freely from a height of a few centimeters above the surface, it would strike the crust at a significant fraction of the speed of light. In practice, no ordinary object could approach so closely and remain intact, but the calculation shows how strong gravity is in this environment. Light itself feels the influence of this compact mass. According to general relativity, gravity curves space-time, and the paths of light rays bend in response. On a neutron star, this effect becomes so pronounced that an observer located far away could see more than half of the surface at once. Light emitted from the far side is bent around the star and redirected toward the observer, producing a distorted view in which the entire sphere seems slightly flattened and enlarged. The star also affects the color and energy of the light. Photons climbing out of the deep gravitational well lose energy, a phenomenon called gravitational redshift. So emitted radiation appears slightly lower in energy than it was at the surface. Newly born neutron stars are also extremely hot. Immediately after formation, they can have interior temperatures of many tens of billions of Kelvin. They cool rapidly at first by emitting neutrinos from the dense interior, then more slowly by radiating heat from the surface in the form of X-rays. For many thousands of years, a young neutron star can remain bright in high-energy light while becoming almost invisible in ordinary visible wavelengths. Embedded in this compact, hot, dense object is another important property: rotation. The original star almost certainly rotated before it collapsed. When the core contracts, its size shrinks by a huge factor, and because angular momentum is conserved, the rotation rate increases. This effect is like that of a spinning object that turns faster when its mass moves closer to its axis. But here it is taken to an extreme. A neutron star can spin many times per second when it is young. Some neutron stars observed as pulsars rotate hundreds of times per second, with rotation periods measured in a few thousandths of a second. This rapid spin is not just a curiosity. It interacts with the star's magnetic field in important ways. The collapsing core drags its original magnetic field inward as it shrinks. Magnetic field lines are squeezed together, and the field strength grows. The magnetic field of a typical neutron star can be trillions of times stronger than the magnetic field at the surface of Earth. In pulsars, this strong magnetic field and rapid rotation combine to create beams of radiation that sweep through space. Charged particles are accelerated along magnetic field lines and emit radiation, especially in radio and high-energy bands. If the rotation axis and magnetic axis are misaligned, the beams do not point in the same direction as the spin. Each time the star rotates, the beams may cross the line of sight of an observer, producing regular pulses of radiation. This lighthouse-like behavior led to the discovery of pulsars in the late 1960s and revealed the presence of neutron stars in the Milky Way. The pulses are remarkably stable in many cases, allowing astronomers to use certain pulsars as precise cosmic clocks. Over long timescales, the rotation gradually slows as energy is radiated away and the pulses lengthen. The observed population of pulsars already shows a variety of spin rates, magnetic field strengths, and emission properties. Within this diversity, there exists a much rarer subtype of neutron star whose behavior cannot be explained by ordinary fields and rotation alone. In these objects, the magnetic field strength appears to be another several orders of magnitude higher than in typical pulsars, reaching values that exceed any other known source. These are magnetars. In them, the combination of gravity, density, temperature, rotation, and especially magnetic field pushes matter and radiation into a regime where established intuition about stars becomes unreliable. Before examining magnetars directly, it is natural to pause on the neutron star stage itself. It is already a dead star that challenges basic expectations, yet it serves as the normal case against which the most extreme versions must be measured. From the calm appearance of distant starlight, stellar evolution has produced a compact object that can bend light-crush matter and generate clock-like flashes, all starting from the same balance of gravity and fusion that once made the star shine. The step from this already extreme endpoint to a magnetar is small in outward appearance, but large in physical consequence, and understanding that step is part of the mystery. Among the many neutron stars born from the deaths of massive suns, only a small fraction appear to follow a rare magnetic path. Most neutron stars behave as expected from the simple picture of a dense, spinning remnant with a strong but not unprecedented magnetic field. Their pulses slow gradually, their emission can often be described by stable beams, and their environments evolve in rough accord with known theory. Against this background, magnetars stand out because their magnetic fields are inferred to be orders of magnitude stronger than those of typical neutron stars, and because their behavior shows intense high-energy bursts, persistent X-ray emission, and irregular timing that cannot be explained by rotation alone. Observations across the Milky Way suggest that only a minority of neutron stars ever pass through such a phase, perhaps roughly 1 in 10 by some estimates. Though the true fraction is uncertain, because many such objects may have already aged and faded beyond easy detection. The path that leads a newly born neutron star into the magnetar state is therefore of particular interest and remains incompletely understood. One family of ideas points to the moment immediately after core collapse, when the remnant is still extremely hot and fluid and spins rapidly. During this brief interval, convective motions and differential rotation within the star can twist and stretch magnetic field lines. If conditions are right, a dynamo process may operate in which moving conductive matter amplifies the magnetic field in a runaway fashion. In this picture, the star starts with a strong but ordinary field inherited from the progenitor, and in only a few seconds, that field is wound up and strengthened to the levels associated with magnetars. The maximum strength reached depends on the initial spin rate, the degree of turbulence, and the structure of the inner layers. If the core rotates sufficiently rapidly and convection is vigorous, the dynamo can turn kinetic energy of motion into magnetic energy with high efficiency. If the rotation is slower or the post-collapse motions are more orderly, the amplification may stall, and the neutron star ends up with a more conventional field. Another family of ideas shifts some of the responsibility back to the life of the parent star before collapse. Some massive stars appear to possess unusually strong magnetic fields during their main sequence lives. In these objects, the field may have been generated earlier in their history or preserved from the birth cloud. When such a star dies, its magnetic field lines are dragged inward during the collapse. Because magnetic flux is conserved in many situations, shrinking the radius of the core by a large factor increases the strength of the surface field by an equally large factor. If the progenitor already carried a particularly strong field, the resulting neutron star could display magnetar-level fields even without extreme dynamo action after the explosion. This scenario suggests that magnetars may be the descendants of a rare subclass of highly magnetized massive stars, and that their scarcity reflects the unusual nature of their parents. Real stars likely combine aspects of both pictures. A strongly magnetized progenitor that also rotates rapidly at core collapse could set the stage for especially efficient field amplification. Conversely, a star with modest or tangled magnetic fields but very rapid rotation might still generate a powerful field through vigorous internal motions. The difficulty is that these initial conditions are not easily recovered from observations made long after the event. By the time a magnetar is detected as an X-ray source, the supernova remnant around it has expanded and cooled, and direct information about the initial spin period or internal structure has been lost. Astronomers therefore rely on indirect clues. The age of the surrounding remnant, the speed and direction of the magnetar's motion through space, and the properties of nearby stellar populations all contribute pieces to the puzzle. When a magnetar is found embedded in a young compact supernova remnant, it suggests that the object is only a few thousand years old and that its intense field has not had much time to decay. When it is located near regions of recent massive star formation, it supports the idea that only stars above a certain mass threshold can produce such remnants. Timing measurements reveal how rapidly the star currently spins and how fast that spin is slowing, which can be compared with theoretical expectations for different initial configurations. In some cases, the inferred birth period is extremely short, pointing to a newly formed neutron star that once spun many times each second. Such rapid rotation would have provided ample energy for a dynamo to act. In other cases, the numbers suggest a more modest birth spin, which is harder to reconcile with the most extreme dynamo models and invites refinements or alternative explanations. There are also suggestions that binary interactions may influence the path to a magnetar. If a massive star has a close companion, tidal forces and mass transfer can alter its rotation rate and internal structure before it explodes. In some scenarios, a merger between two stars or between a star and a compact object can produce a core with unusual spin and composition, primed for intense magnetic amplification. After the explosion, the companion may be ejected or may remain in a wide orbit, leaving signatures in the motion and environment of the magnetar. A few observed systems hint at such complex histories, though none yet provide complete certainty. Across all these possibilities, a pattern emerges in which magnetar formation depends sensitively on conditions during a brief and inaccessible period of a star's life. Small differences in spin field geometry or internal turbulence may decide whether the remnant follows the common path of an ordinary neutron star or enters the extreme magnetic state. Because that decision is made deep inside an opaque stellar core, and over only a short time direct observation is impossible with current instruments. Instead, researchers build numerical models of core collapse and neutron star birth adjusting parameters until the resulting objects resemble the magnetars that are actually seen. These models can reproduce many features, such as strong fields and rapid early spin down, but they also reveal tensions, such as the need for finely tuned initial conditions. The growing catalog of known magnetars provides additional constraints. Their locations in the galaxy, the ages of their associated remnants, where these can be measured, and the energies of their bursts all paint a picture of a population that is young on astronomical timescales, often found in or near star-forming regions, and capable of releasing extraordinary amounts of energy in a short time. Yet they are not all identical. Some display persistent X-ray emission without frequent giant flares. Others show occasional bursts and long periods of relative quiet. Some have spin periods clustered in a narrow range of several seconds, which is unusual compared to the broad distribution of pulsar periods. This clustering may indicate that magnetars are born spinning rapidly but slow quickly as their enormous fields extract rotational energy. If so, the magnetar phase could be a transient episode in the life of many neutron stars, visible only while the field is strongest and the rotation is still being braked. Once the field decays or the star slows enough, the object might begin to resemble a more ordinary neutron star blending into the background population. In that case, many former magnetars could be hidden among apparently normal remnants, their extreme past marked only by subtle differences in composition or internal structure. At present, the evidence is not decisive. Theoretical work continues to refine the picture, and new observations slowly expand the sample of known magnetars. Each new detection offers a slightly different combination of age, environment, and behavior, and with each one, the simple pathways sketched in early models tend to become more intricate. What began as a straightforward question about why some neutron stars are more magnetic than others has expanded into a broader puzzle of how mass rotation, field inheritance, binary interaction, and stochastic processes and turbulence combine in the final seconds of a massive star's life. The answer is still forming, and the partial explanations currently in use serve as scaffolding around a structure whose full shape is not yet visible. In this uncertainty lies part of the interest in magnetars. They are not only extreme endpoints of stellar evolution, but also sensitive probes of conditions that cannot be replicated in laboratories. The fact that only a few follow this rare path makes them all the more valuable and all the more puzzling. They stand as outliers among neutron stars, hinting at hidden diversity in how massive stars die and in what their cores become. A magnetar viewed from a safe distance in space appears at first like a small intense point of high-energy light buried deep within the crowded field of the Milky Way. Its diameter is only a few tens of kilometers, yet its mass is similar to that of the Sun, and its gravity shapes the behavior of light itself. Photons that pass near the surface do not travel in straight lines. Instead, their paths curve in the warped space-time around the compact star. This bending means an observer far away can see more than half of the magnetar's surface at once. Light from the far side arcs over the limb and reaches the distant detector. The star seems slightly enlarged and flattened, with its edges blurred by gravitational lensing. At the same time, the energy of the light changes as it fights its way out of the deep gravitational well. Radiation emitted from the surface in a given color is shifted to lower energy as it climbs, so the spectrum that arrives at telescopes is subtly redder than the spectrum at the surface. The surface itself is far from quiet. Temperatures can reach several million Kelvin. At such temperatures, the thermal radiation peaks in the X-ray band, so in most observing campaigns, magnetars are strongest in X-rays, with some contribution in soft gamma rays. In visible light, they would appear white, because the combined emission across blue and red bands blends together, but their optical brightness is modest compared to their X-ray output. Around them, the remains of the supernova that gave birth to the neutron star may still glow in expanding filaments of gas, but the central object is distinguished by its hard, penetrating radiation. Beneath that radiant surface lies a solid crust made of nuclei and electrons arranged in a crystalline lattice. This crust is only a thin outer layer compared to the star as a whole, yet it plays a central role in magnetar behavior. Gravity is so strong that the tallest structures the crust can support are no more than a few centimeters high. In effect, the most prominent mountains on a magnetar are smaller than a hand on Earth. Any attempt to build a taller peak would be crushed almost instantly by the weight of the overlying matter. The surface is smooth, hard, and under immense stress from below and above. Above, gravity presses inward. Below, the dense, neutron-rich interior presses outward, and the magnetic field threads through everything, exerting its own forces on the charged components of the matter. The magnetic field inside a magnetar is not necessarily uniform. Theory suggests that it can wrap around itself, twist, and form complex patterns. In some models, the interior field is even stronger than the field that threads through space outside. As the field evolves and tries to relax into a lower energy configuration, it pushes on the crust. Over time, this slow rearrangement of field lines builds up stress in the solid outer layer. The crust can deform to accommodate some of this stress, but only up to a point. When the stress becomes too great, the crust fractures. These events are called starquakes, by analogy with earthquakes on a planet, but the energies involved are vastly greater, and the environment in which they occur is far more extreme. In a starquake, a patch of crust suddenly shifts, releasing elastic energy and allowing the local magnetic field to rearrange. That rearrangement triggers a reconfiguration of the magnetosphere, the region of space around the star dominated by its magnetic field. In this process, charged particles are accelerated to relativistic speeds and strong electric fields are induced. The outcome is a burst of radiation, often in the form of hard X-rays and gamma rays. Some magnetars display frequent, relatively modest bursts that last fractions of a second. Others occasionally produce intermediate events of higher energy. Rarely a magnetar releases a giant flare in which a huge amount of energy emerges in a single brief outburst. One such event detected in the early years of this century from a magnetar located tens of thousands of light years away briefly dominated the high-energy sky. Earth-orbiting satellites recorded a sudden spike of gamma rays that saturated some instruments and forced others into protective modes. Analysis of the data suggested that in less than a second, the magnetar emitted as much energy in high-energy radiation as the sun radiates in all wavelengths over a span of many tens of thousands of years. At that distance, the pulse posed no direct hazard to life on Earth, but calculations showed that if a similar flare occurred within roughly 10 light years, the high-energy photons could significantly damage the ozone layer in the upper atmosphere with consequences for surface life. The rarity of such events and the scarcity of magnetars make this a low-probability threat on human timescales, yet the possibility emphasizes how powerful these objects are. The detailed light curves of giant flares reveal further clues. Some show a very bright short initial spike, followed by a decaying tail of emission, modulated at the magnetar's rotation period. Superimposed on this tail, subtle quasi-periodic oscillations appear with frequencies that may correspond to seismic vibrations in the star's crust, or even to oscillations in deeper layers. These features suggest that starquakes can excite global modes in the magnetar, causing it to ring like a bell at characteristic frequencies. By studying these oscillations, researchers hope to probe the interior structure of neutron star matter. However, the mapping between observed frequencies and internal properties is not straightforward, because the behavior of superdense matter and strongly magnetized elastic media is not yet fully known. Some models imply that the crust and the nuclear pasta in the inner layers can support particular shear modes. Others incorporate the coupling between crust and core through magnetic field lines, which alters the spectrum of vibrations. The observed quasi-periodic signals appear in some flares, but not in others, and their exact frequencies vary from event to event. This inconsistency presents another puzzle. If magnetars always responded to starquakes in the same way, their seismic signatures would be more uniform. Instead, each flare seems to carry a distinct pattern, hinting that the internal field structure and the distribution of stresses change as the magnetar ages. Even the occurrence of starquakes is irregular. Magnetars can remain relatively quiet for years, emitting steady X-rays powered by the slow decay of their magnetic fields and by residual heat from their formation. Then, with little warning, they can enter an active period producing bursts and flares over days or weeks. Afterward, they may subside again into a quieter phase. The triggers for these transitions are not fully understood. One line of thought suggests that the internal magnetic field gradually drifts and rearranges, altering the stresses until a critical threshold is reached. Another possibility is that external interactions such as accretion of material or changes in the surrounding plasma might occasionally perturb the magnetosphere, but for many magnetars there is no evidence of significant accretion. The randomness in timing and intensity of bursts makes it difficult to predict when a given magnetar will flare. Instruments in orbit monitor the sky continuously in X-rays and gamma rays, and automated systems alert astronomers when a sudden burst appears. When the position of the burst is traced back to a known magnetar, or when repeated bursts from the same location allow a new magnetar to be identified, the surface and crustal processes of that object become a focus of study. Each new observation tests current ideas about how starquakes work and how the magnetic field and crust communicate. There is also the question of how much the crust can change over time. If repeated fractures occur in the same regions, they could gradually alter the composition and structure of the outer layers. If the magnetic field relaxes into a simpler configuration after many rearrangements, the rate of star quakes might decrease, ushering the magnetar into a more stable, less active phase. Observational hints point toward such an evolution, but the timescales involved are long compared to human lifetimes, and the number of systems available for study is still small. What is evident is that the surface and crust of a magnetar are not passive boundaries. They are dynamic, stressed interfaces between the vacuum outside and the exotic matter within, continually shaped by gravitational curvature and magnetic tension. When they fail, they do so in a way that briefly floods space with high-energy light. Those flashes, crossing thousands of light years, carry detailed information about the state of the star at the moment of fracture, but they also raise new questions about what is happening under the surface where direct observation cannot yet reach. Beneath the solid crust of a magnetar, the familiar language of atoms and ordinary matter steadily loses its usefulness. The outermost crust consists of atomic nuclei and electrons arranged in a regular lattice. In this region, nuclei are still recognizable clusters of protons and neutrons, although they are more neutron-rich than in most materials on Earth, because the intense gravity and high pressure favor the presence of neutrons. Electrons move freely between these nuclei, forming a degenerate electron gas that helps carry electrical current and heat. As depth increases, pressure grows, and nuclei are forced closer together. Neutrons begin to drip out of the nuclei, forming a fluid that surrounds and permeates the lattice. This marks the transition to the inner crust, where the matter becomes an interpenetrating mixture of nuclei-free neutrons and electrons. The density here approaches that of atomic nuclei, and the competition between nuclear attraction, nuclear repulsion, and the constraints of quantum mechanics creates structures that are not seen anywhere else in nature. The forces between nucleons favor certain separations and arrangements. When the density is not quite high enough for matter to become a uniform fluid, energy can be minimized by forming intermediate shapes. Instead of isolated spherical nuclei, matter organizes into extended structures. Calculations suggest that at certain depths, the protons and neutrons clump into roughly spherical blobs embedded in the neutron sea. This phase has been given the informal name of nuclear gnocchi. At higher densities, these blobs merge into elongated filaments, a phase sometimes called nuclear spaghetti. Deeper still, the filaments broaden and merge sideways into sheets of nuclear matter, referred to as nuclear lasagna. Beyond that, the order can reverse with voids and tubes forming in an otherwise uniform background, leading to more phases with descriptive labels. Collectively, these structures are known as nuclear pasta, and although the names are light in tone, they refer to specific predicted configurations resulting from the balance of forces in this peculiar environment. The existence of nuclear pasta is not yet confirmed directly by observation, but it arises naturally from many numerical simulations of dense matter. It is a consequence of the densities and pressures expected in neutron star crusts and core boundaries, and of the known properties of the strong nuclear interaction. In a magnetar, the presence of an intense magnetic field complicates this picture further. Charged components, such as protons and electrons, respond strongly to the field, while neutrons respond indirectly through their magnetic moments. The field can influence how currents flow and how structures align, potentially distorting the ideal configurations found in simulations without magnetic effects. It may favor certain orientations of the pasta structures or cause anisotropies in mechanical and thermal properties. Because magnetar crusts are subject to enormous magnetic stresses, the detailed arrangement of nuclear pasta could affect how the crust yields and fractures, and therefore how star quakes unfold. Beneath the inner crust, matter reaches densities where individual nuclei dissolve. Neutrons and the remaining protons merge into a more uniform fluid. In this outer core region, the matter is mostly neutrons with a fraction of protons, electrons, and possibly muons to maintain charge balance. Under such conditions, neutrons are thought to form a superfluid. A superfluid is a phase of matter that flows without viscosity and exhibits macroscopic quantum behavior. Protons may become superconducting, meaning they can carry electrical current without resistance. These phases are expected because of the attractive interactions between particles at certain momenta and the extreme densities present. The coexistence of neutron superfluidity and proton superconductivity threaded by a strong magnetic field gives the magnetar core a complex interior dynamics. Rotational angular momentum in a superfluid is carried not by ordinary swirling flows, but by quantist vortices, thin tubes around which the fluid circulates in discrete amounts. In a superconducting region, magnetic flux may be confined to quantized tubes known as fluxoids. The interaction between neutron vortices and proton flux tubes can couple the rotation of the superfluid to the magnetic structure. When vortices move or are pinned and then suddenly unpin, they can alter the spin of the star in abrupt steps, phenomena observed as glitches in some neutron stars. In magnetars, where the magnetic field is much stronger than average, the coupling between vortices and flux tubes could be particularly intense, possibly influencing both timing irregularities and the evolution of the field itself. Going inward, the density eventually reaches and may exceed the density of atomic nuclei. At this point, the behavior of matter is uncertain. Various theoretical models explore different possibilities. In one class of models, the core remains a fluid of neutrons, with a small admixture of protons and other particles, with interactions described by effective nuclear forces calibrated against experiments on atomic nuclei. In another class, more exotic components appear, such as hyperons, which are particles containing strange quarks, as well as up and down quarks, or condensates of mesons. In yet another possibility, the quarks themselves no longer remain locked inside individual neutrons and protons, and the matter transitions to deconfined quark matter. In some versions of this scenario, quarks pair in ways that lead to color superconductivity, an analog of superconductivity in which color charge, rather than electric charge, is involved. If strange quarks are present in comparable numbers, the core might become a form of strange quark matter, which some theories consider potentially more stable than ordinary nuclear matter. In a magnetar, the immense magnetic field could influence any of these phases, modifying their properties and making them anisotropic. Observational access to these inner regions is limited. No instrument can see inside a neutron star directly. Instead, constraints arise from macroscopic properties such as mass radius and response to stress. Precise measurements of neutron star masses in binary systems show that at least some neutron stars can support masses around 2 times that of the Sun, or slightly higher. This requirement rules out some equations of state, the relations between pressure and density for dense matter that are too soft to support such heavy stars. Radius measurements drawn from X-ray observations of thermal emission and from modeling of bursts suggest typical values in a range of around 10 to 15 kilometers, although uncertainties remain. The combination of high maximum masses and modest radii implies that dense matter must be stiff enough at certain densities to bear great weight, yet not so stiff at lower densities that the radii become too large. This balance restricts the set of allowed internal compositions, but does not uniquely determine it. Additional information comes from observations of oscillations and glitches. The quasi-periodic oscillations seen in magnetar giant flares likely involve vibrations that penetrate into the crust and perhaps the core. Their frequencies and damping times carry imprints of how rigid and how coupled different layers are. Rotational glitches, sudden changes in spin rate, reveal that the interior contains components that can store and release angular momentum in ways decoupled from the crust. Both types of phenomena require superfluidity and elasticity features that any viable model must include. Yet, even when all these constraints are applied, multiple models can still fit the data leaving room for very different internal arrangements. Gravitational wave observations from merging neutron stars add new information. When two neutron stars spiral together and collide, their mutual gravity tidally deforms them. The degree of deformation depends on how easily their matter can be stretched, which in turn depends on the equation of state. The wave form of the gravitational waves carries signatures of this tidal response. Analyses of such events have already ruled out some very stiff or very soft equations of state, narrowing the space of possibilities. However, magnetars as such have not yet been caught in mergers, and their distinctively strong magnetic fields may alter their internal structures compared to more typical neutron stars. For magnetars specifically, the persistent high-energy emission and the pattern of outbursts suggest that their interiors are still evolving energetically. The decay of the magnetic field converts magnetic energy into heat, keeping the star warmer for longer than ordinary neutron stars of similar age. That heat flows outward, affected by the thermal conductivity of the nucleopasta and core phases. If nucleopasta is highly conductive along some directions and less so along others, it could channel heat in preferred paths, leading to temperature variations across the surface. Some X-ray observations of magnetars reveal hotspots and non-uniform emission, which may be the surface expression of such internal anisotropies. In combination, these hints create a layered view of magnetar interiors, a thin, stressed solid crust overlying a region of nuclear pasta, below which lies a superfluid and superconducting outer core, and beneath that, a potentially exotic inner core of uncertain composition. Each layer has its own characteristic scales and behaviors, yet they are all coupled through gravity and the magnetic field. Stress in one region can propagate and find release in another. A crustal fracture can adjust magnetic field lines that are anchored deeper down. A gradual rearrangement of the internal field may change the rate at which heat is delivered to the crust. Despite the detailed models, many aspects of this picture remain speculative. Nucleopasta has not been imaged or sampled. Its presence is inferred from theory, and its properties are still being refined. The true nature of the inner core is highly uncertain because It involves physics at densities and conditions beyond the reach of existing experiments. Even the precise strengths and configurations of magnetar internal fields are unknown. Observationally measured values refer primarily to the large-scale dipole component, while the internal toroidal components could be much stronger. The fact that such a complex and poorly known structure can nonetheless be packaged into an object only a few tens of kilometers across, and that this object can produce observable signals across the galaxy, demonstrates how tightly matter is compressed in a magnetar. It also means that each new piece of data, whether from timing spectra bursts or gravitational waves, can have disproportionate impact on our understanding. The layers from crust to core are not just static ingredients, but active participants in the magnetar's ongoing evolution, and the current set of models is likely only a first approximation to the true internal landscape. Among all known astronomical objects, magnetars stand out as the strongest naturally occurring magnets. To describe their fields, physicists use a unit called the Tesla, which measures magnetic field strength in a way that can be compared from everyday life to cosmic extremes. The magnetic field at the surface of Earth is about 50 microtesla, enough to guide compasses and shape auroras, but too weak to affect ordinary objects in daily experience. A typical fridge magnet has a strength of a few millitesla. Special industrial and medical magnets, such as those used in magnetic resonance imaging machines, reach several tesla and require heavy engineering and careful safety procedures because they can pull metal objects from across a room. The most powerful continuous magnets built in laboratories can reach tens of tesla. These devices represent the limits of controlled human technology. Against this scale, the magnetic field of a magnetar is difficult to grasp. Inferred field strengths lie in a range between about 100 million tesla and 100 billion tesla. This means that a magnetar can be billions of times more magnetic than any laboratory device and many orders of magnitude stronger than Earth's field. These values are not guessed. They arise from measurements of how quickly the magnetar's spin slows down and from models of how magnetic braking extracts rotational energy. The fact that the spin-down rates are so high in some neutron stars implies that their magnetic fields must be correspondingly strong. In some cases, the inferred dipole field at the surface approaches or exceeds a value at which quantum effects in the vacuum become important, a threshold sometimes called the quantum critical field. In such regimes, the magnetic field is no longer simply a background influence on charged particles. It becomes an active participant in shaping how light and matter behave. One way to understand the impact of such a field is to consider what it would do to matter brought into its vicinity. At distances of thousands of kilometers from the magnetar, the field is still strong enough to affect atomic structure. The magnetic forces on the electrons and atoms become comparable to or greater than the electrical forces that normally bind those electrons to nuclei. Under these conditions, atomic orbitals, which are usually roughly spherical or mildly distorted shapes, are stretched and compressed. Calculations indicate that atoms aligned with the field lines can become elongated like thin needles, with lengths far greater than their widths. The energy levels of electrons are quantized differently, leading to a set of allowed states known as Landau levels. Molecules cannot easily form in the familiar way because the shared electron clouds that hold them together are distorted. Solid matter exposed to such fields would not behave like the solids experienced in human environments. Its electrical and thermal properties would be dominated by the imposed magnetic direction. The effect is not limited to electrons. Ions and charged fragments follow tight spirals around field lines, and their motion across those lines is strongly constrained. The result is a medium in which transport processes, such as heat flow and particle diffusion, can become highly directional, favoring motion along the field and suppressing it across the field. If an ordinary object, such as a spacecraft or a rock, could somehow approach within 1,000 kilometers of a magnetar without being disrupted by tidal gravity, the magnetic forces would be intense enough to pull on the charges in its constituent atoms and exert differential forces between one side and the other. Estimates suggest that these forces would be sufficient to tear the object apart at the atomic level. In practice, no known material could maintain its integrity under such conditions. The influence of magnetar fields extends beyond matter to the quantum vacuum itself. In quantum field theory, what appears as empty space is not truly empty. It is filled with fluctuating fields and virtual particle pairs that pop into existence and vanish again. In ordinary circumstances, these fluctuations have subtle effects that are hard to detect. However, when the magnetic field approaches the quantum critical value, it can polarize the vacuum, aligning the virtual pairs and changing the way light propagates. This phenomenon, called vacuum birefringence, is analogous in concept to the way certain crystals split light into two beams with different polarizations and slightly different speeds. In the magnetar case, the strong field causes different polarizations of light to experience slightly different refractive indices, even though they are traveling through what would otherwise be considered empty space. As a result, light emerging from the environment around a magnetar can have its polarization state altered in characteristic ways. Modern X-ray polarimetry missions and optical observations of highly magnetized neutron stars have begun to find evidence consistent with such effects, although the measurements are challenging and their interpretation requires careful modeling. If confirmed, these observations would provide a direct window into a regime of quantum electrodynamics that cannot be reproduced on Earth. At even higher field strengths, further exotic processes are predicted. Photons moving through a sufficiently strong magnetic field can, in principle, split into two lower energy photons, or decay into pairs of electrons and positrons, the antimatter counterparts of electrons, if conditions permit. These processes, while rare, could contribute to the rich structure of magnetar magnetospheres by supplying pairs of charged particles that then radiate and participate in current flows. The observed spectra of magnetars with combinations of thermal components from the surface and non-thermal tails extending to higher energies suggest that multiple emission processes are present. Resonant scattering of surface photons by charges in the magnetosphere, pair cascades, and magnetic reconnection are all parts of current models. However, disentangling their contributions remains difficult, in part because the parameters of the magnetic field, such as its strength and geometry at different locations, are not known precisely. The magnetic field also stores energy. In a magnetar with a surface field of around 100 million Tesla and stronger internal components, the total magnetic energy contained within the star and its magnetosphere can be immense, comparable to or exceeding the rotational energy of the star. As the field evolves and decays over thousands to hundreds of thousands of years, that energy must be released. Some is converted into high-energy radiation during bursts and flares. Some is converted into heat within the interior, keeping the magnetar warmer for longer than a non-magnetic neutron star of the same age. Some may go into accelerating particles and driving outflows that carry energy into the surrounding space. The exact partition is not known. What is clear is that the decay of the magnetic field is not a smooth, uniform process. Instead, it appears to proceed in episodes with quiet intervals, punctuated by sudden rearrangements and energy releases. The way in which magnetic energy is distributed between large-scale dipole components and smaller-scale internal structures likely affects the surface behavior. A magnetar whose magnetic field is mostly arranged in a simple dipole might spin down in a predictable way and radiate relatively steadily, whereas one with strong twisted internal fields may be prone to frequent crustal fractures and magnetospheric outbursts. Observationally, the known magnetars span a range of behaviors hinting that their internal magnetic architectures are diverse. There is also the question of whether there exist objects with magnetic fields even stronger than those already inferred, perhaps formed in particularly energetic events, such as certain kinds of superluminous supernovae or in the aftermath of neutron star mergers. Some theoretical models invoke ultra-magnetized neutron stars to power the most luminous gamma-ray bursts and certain types of fast-evolving transients. In those scenarios, the newborn object may have a magnetic field and rotation rate so extreme that it loses most of its rotational energy within a short time, driving a powerful outflow before collapsing further into a black hole. If such hypermagnetized phases occur, they may be brief and largely hidden from direct observation, leaving behind magnetars or black holes that have already shed their most dramatic magnetic energy. For now, the magnetars observed in the Milky Way and nearby galaxies represent the most accessible examples of nature's strongest magnets, and they occupy an important niche in the landscape of high-field phenomena. In this context, magnetars function as laboratories for physics in extreme magnetic regimes. They test how matter behaves when atoms are distorted, how the vacuum responds when quantum fluctuations are aligned, and how magnetic fields evolve when their energy density rivals or exceeds that of the matter that generates them. Each measurement of a magnetar's spectrum polarization and timing adds a piece to the picture, yet the pieces do not yet fit into a single, simple pattern. The combination of strong fields, rapid rotation in early life, complex interior structure, and external plasma flows produces a system with many degrees of freedom. The current models are necessarily simplified, and their success at reproducing some aspects of magnetic behavior can obscure the fact that other aspects remain unexplained. The extreme magnetic fields themselves, so central to the identity of magnetars, thus remain both a tool for probing fundamental physics and a source of ongoing uncertainty about how such fields are generated, how they are structured, and how they ultimately fade. When magnetars release their stored magnetic energy in sudden events, the resulting outbursts can briefly rival the output of entire galaxies in the most energetic forms of light. These episodes, known as bursts and giant flares, first attract attention as sudden spikes in gamma-ray detectors that watch the sky almost continuously. Many such detectors are mounted on satellites, though, whose primary missions may be solar monitoring, high-energy astronomy, or even planetary exploration. But their instruments are sensitive to brief flashes from any direction. When a magnetar becomes active, these instruments record a sharp increase in count rate, sometimes so large that their electronics saturate, followed by a tail of decaying emission. The first recognized events of this kind were detected in the late 1970s from sources that later become known as soft gamma repeaters. Initially, the bursts appeared as isolated flashes of soft gamma rays and hard X-rays lasting a fraction of a second to a few seconds. Over time, repeated outbursts from the same sky locations revealed that these were not one-time explosions, but recurring phenomena. The association of soft gamma repeaters with young neutron stars and supernova remnants led to the idea that they might be highly magnetized neutron stars. Only later did the magnetar model emerge as a coherent framework connecting their bursting behavior to ultra-strong magnetic fields. A typical short burst from a magnetar releases an amount of energy comparable to that emitted by the sun in many years. Yet the event lasts only a small fraction of a second and is confined to a small region near the star. The bursts occur in clusters during active episodes, with dozens or hundreds detected over days or weeks. Their spectra, the distribution of photon energies, often show a quasi-thermal component that can be modeled as emission from a hot patch on the surface, combined with a harder tail thought to arise from scattering and acceleration in the magnetosphere. The rise times are extremely fast, indicating that the energy release mechanism operates on timescales comparable to the light crossing time of the magnetosphere. Yet despite their intensity, these short bursts are modest compared to the rare giant flares. Giant flares are distinguished by an initial spike that can outshine almost everything else in the gamma-ray sky, followed by a decaying tail modulated at the magnetar's rotation period. One of the most thoroughly studied examples occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, in the late 1970s. Another came from a magnetar in our own galaxy in the late 1990s. The most dramatic event so far recorded arrived in late December of the year 2004 from a magnetar designated with a name that encodes its sky coordinates. This object lies at a distance of roughly 40,000 light-years from Earth, on the far side of the Milky Way. When it flared, satellites in Earth orbit spacecraft throughout the solar system, and even instruments on the Moon recorded the burst. The initial spike lasted only a fraction of a second, but delivered so much energy that it briefly altered the ionization state of Earth's upper atmosphere. Some detectors were driven into protective shutdown modes by the intensity of the incoming radiation. From the measured flux at Earth and the estimated distance, astronomers inferred that in that brief interval, the magnetar emitted an amount of energy comparable to what the sun would radiate over a span of roughly 150,000 years. The decaying tail that followed lasted several minutes. Its brightness rose and fell periodically, with the period corresponding to the magnetar's rotation. Superimposed on this modulation were smaller oscillations at higher frequencies. These features, interpreted as vibrations of the crust and possibly deeper layers, provided the first opportunity to practice a kind of seismic probing on a neutron star. The giant flare thus served both as a spectacular display of magnetic energy release and as a diagnostic tool for the star's interior. Yet the event also raised questions. Why did the magnetar flare so dramatically at that particular time after years of relative quiet? Why did the energy partition into a brief, intense spike and a longer, modulated tail? Theories of giant flares invoke the sudden reconnection of magnetic field lines in a twisted magnetosphere combined with a major fracture in the crust, or a rapid reconfiguration of the internal field. In some models, a bundle of magnetic field lines anchored to the crust becomes wound up over time, storing energy in its twist. When the twist exceeds a stability threshold, the field reconnects, releasing energy and accelerating particles. The sudden change in magnetic stress then cracks the crust, exciting seismic modes that ring down in the tail. These ideas reproduce many qualitative features, but the details, such as the exact energies, durations, and oscillation spectra, depend sensitively on assumptions about field geometry and crustal properties that are not directly constrained. The recurrence pattern of giant flares is also puzzling. Only a few have been observed in several decades of monitoring, despite the growing number of known magnetars and the large volume of sky under surveillance. This rarity suggests that giant flares are genuinely exceptional events, perhaps representing major reorganizations of the magnetic field that occur only a few times in a magnetar's lifetime. If so, the observed sample may be an incomplete record of a process that over hundreds of thousands of years could gradually dissipate much of the internal magnetic energy. On the other hand, selection effects may hide some flares. A giant flare in a distant galaxy might appear to detectors as a short, intense burst of gamma rays without a clearly detectable tail. Such signals would be categorized as short gamma ray bursts, a class of events also produced by mergers of compact objects. Distinguishing magnetar giant flares from distant mergers based solely on their prompt emission is difficult. Some short bursts observed in nearby galaxies with associated star formation have properties that resemble scaled versions of known giant flares, leading to the suggestion that magnetars may contribute to the population of short gamma-ray bursts. If this is correct, magnetars would occasionally make themselves known across cosmological distances, their flares appearing as brief flashes in external galaxies. The connection between magnetar activity and other transient phenomena has grown more intricate with the discovery of fast radio bursts, millisecond-long flashes of radio waves originating at extragalactic distances. In one notable case, a fast radio burst-like event was detected from a magnetar in the Milky Way during an active period, suggesting that at least some fast radio bursts may be produced by magnetar processes. However, most fast radio bursts come from far beyond the Milky Way, and their repetition patterns, energies, and environments vary widely. Magnetars are a natural candidate to power them because of their stored magnetic energy and their known ability to generate sudden outbursts. Models propose that crustal fractures, magnetospheric reconnection, or interactions with surrounding material could produce coherent radio emission under certain conditions. Yet, not all magnetars observed during active periods emit detectable fast radio bursts, and not all extragalactic fast radio bursts show parallel high-energy activity. This mismatch hints at a diversity of conditions or at different subclasses of sources. Within the magnetar bursting behavior itself, there are anomalies that resist simple classification. Some magnetars display so-called anti-glitches, sudden spin-down events, rather than the more common spin-ups. Others show changes in pulse, shape, and spectrum that persist long after a burst episode has subsided, as if the magnetosphere has settled into a new configuration. There are cases where the persistent X-ray luminosity rises sharply following an outburst and then decays over weeks to months, indicating the deposition of heat in the crust and its subsequent diffusion outward. The shapes of these decay curves and the distribution of surface hotspots inferred from spectral modeling provide clues about where and how energy was injected. Yet each event seems to have its own particulars. Even the relation between magnetic field strength and bursting activity is not straightforward. Some neutron stars with inferred magnetic fields lower than the canonical magnetar range have exhibited magnetar-like bursts, while some with high fields have remained quiet for as long as they have been monitored. This blurs the boundary between magnetars and other neutron stars and suggests that field configuration age and internal structure may matter as much as or more than the simple field strength. From an energy accounting perspective, each burst and flare removes some magnetic energy from the system, but the total budget remains large. The observation of magnetars at different apparent ages with varied levels of activity indicates that magnetic field decay is a long, uneven process. It may proceed rapidly during youth, when the internal field is strongest and the crust is more pliable, then slow as the star cools and the field relaxes. Alternatively, it may be punctuated by rare giant reorganizations. In either case, the bursts and flares represent momentary glimpses into the stages of this decay. They are unstable episodes in a gradual transformation from an initially extreme magnet to a quieter, less magnetically stressed object. Each recorded outburst therefore serves a dual role. It provides data that can be used to infer conditions in the magnetar at that time, and it marks another small step in the long-term evolution of the star. Taken together, the catalog of bursts and giant flares displays patterns of energy timing and spectral shape that partially align with models of magnetic stress and crustal failure, yet also contain irregularities and exceptions. The most powerful events challenge assumptions about limits on energy storage and release, and their possible links to fast radio bursts and short gamma-ray bursts connect magnetar physics to broader questions in high-energy astrophysics. In this way, the bursting behavior of magnetars acts as both a local probe of their immediate environment and a bridge to phenomena occurring across cosmic distances, all emerging from the interplay of dense matter and intense magnetic fields in a sphere the size of a city. The study of magnetars depends on instruments that turn brief and distant disturbances in high-energy light into detailed records that can be examined long after the events themselves have faded. Space-based observatories operated by agencies such as NASA and the European Space Agency carry detectors for X-rays and gamma rays that survey large portions of the sky. Some, like dedicated gamma-ray burst monitors, continuously watch for sudden increases in count rates, triggering automatic alerts when thresholds are crossed. Others, like pointed X-ray telescopes, focus on specific sources but can be redirected when an interesting event occurs. When a magnetar becomes active, the first indication often arrives as an automated signal, a notification that a high-energy instrument has registered a flare from some region in the sky. Ground-based networks receive these alerts, and observatories around the world turn their attention to the source attempting to capture the aftermath across multiple wavelengths. In this way, individual outbursts from magnetars become global observing campaigns. Once a magnetar has been identified, its persistent emission can be monitored in quieter times. X-ray telescopes record spectra that show how the intensity of the radiation varies with photon energy. Simple models often represent this emission as a combination of a thermal component arising from a hotspot or a broader warm region on the surface and a non-thermal component produced by scattering and acceleration in the magnetosphere. Over months and years, repeated measurements track how these components change as the magnetar cools and as its magnetic field evolves. Small shifts in the temperature and size of the inferred hotspots or in the slope of the non-thermal tail may indicate changes in the distribution of currents and twists in the external field. When a burst episode erupts, new spectra taken during and after the event can be compared with the earlier baseline, revealing how much energy has been added to the crust and how the magnetosphere has been reorganized. Timing measurements add another layer of information. By recording the arrival times of individual photons and folding them at trial periods, astronomers construct pulse profiles that show the average light curve over a single rotation of the star. Some magnetars have relatively simple profiles with one or two broad peaks per rotation. Others display complex structures with multiple subpulses. The shapes of these profiles depend on the geometry of the magnetic field, the distribution of hot regions on the surface, and relativistic effects such as light bending. In principle, by fitting detailed models to observed pulse profiles, it is possible to infer the angles between the rotation axis, the magnetic axis, and the line of sight, as well as the size and location of emitting areas. In practice, the problem is degenerate, but it remains a powerful tool. Changes in pulse shape following an outburst suggest that the surface emission pattern or the magnetospheric configuration has altered. For example, a hotspot may have expanded or shifted, or a twisted bundle of magnetic field lines may have untwisted, changing where currents flow. Long-term timing also reveals how the spin of the magnetar evolves. Measurements of the rotation period and its derivative over years and decades show that magnetars spin down more rapidly than most pulsars consistent with their strong magnetic fields. However, this spin down is not perfectly smooth. Sudden changes, including glitches and anti-glitches, and periods of enhanced torque during active episodes, indicate that angular momentum exchange between the crust, the superfluid interior, and the magnetosphere is complex. By correlating timing irregularities with episodes of bursting or spectral hardening, researchers search for patterns that might link internal processes to external behavior. Sometimes, a major outburst coincides with a measurable jump in spin parameters. In other cases, timing changes occur without obvious radiative signatures. These mismatches remind investigators that the star's interior can rearrange in ways that are only partially visible in electromagnetic emission. Beyond the X-ray and gamma-ray bands, other windows on magnetars are more challenging but equally informative. In radio wavelengths, a few magnetars have been observed to emit pulsed signals similar to those of ordinary radio pulsars, but with important differences. Their radio emission often appears only during or shortly after X-ray active phases, and their spectra and variability differ from those of standard pulsars. The emergence and disappearance of radio pulses from magnetars suggest that their magnetospheres can switch between different states, some conducive to coherent radio emission and others not. Observations with large radio telescopes and interferometric arrays follow these changes, trying to map out the conditions under which a magnetar becomes radio loud. The connection between magnetar radioactivity and fast radio bursts adds further motivation, as any detailed link would help clarify the origins of these brief, extragalactic flashes. Optical and infrared observations, though difficult, because magnetars are faint at these wavelengths and often lie behind dense interstellar dust, have yielded detections in some cases. In a few magnetars, infrared emission appears to trace a surrounding disk of material, perhaps the remnant of the supernova fallback that did not escape the system entirely. Such disks, if present, could interact with the magnetar's strong field and outflows influencing its spin and emission. In other cases, near-infrared light seems more likely to be magnetospheric in origin, extending the non-thermal spectrum observed at higher energies. Monitoring these faint signals before and after X-ray outbursts can reveal whether they brighten and fade in step with high-energy activity or respond on different time scales, offering clues to where in the system the emission arises. One striking class of observations comes from scattered light echoes. When a giant flare or bright burst from a magnetar propagates through the surrounding interstellar medium, some of its X-rays are scattered by layers of dust along the line of sight. Because the scattered photons travel slightly longer paths, they arrive later than the direct ones. As a result, expanding rings of X-ray light can appear around the source in images taken hours to days after the flare. The angular size of these rings increases with time, and their brightness and spectrum carry information about the distribution and composition of the intervening dust. In at least one celebrated case, such rings were observed around a magnetar that had just produced a major outburst. By modeling the geometry of the dust layers and the timing of the rings, astronomers were able to refine the distance to the magnetar and to trace structures in the interstellar medium along that particular sightline. These light echoes show how magnetar outbursts can temporarily illuminate and probe the otherwise invisible dust between stars. New kinds of instruments open further possibilities. X-ray polarimeters designed to measure the preferred orientation of the electric field vectors of incoming photons are now capable of detecting the polarization of light from neutron stars. Magnetar emission, shaped by strong fields and potentially by vacuum birefringence, is expected to be highly polarized in ways that depend on field geometry and viewing angle. Early polarimetric measurements of highly magnetized neutron stars have begun to show signatures consistent with strong field effects, though the sample is still small and the interpretation requires careful modeling of both the surface emission and propagation through the magnetosphere. As more data accumulate, the hope is that polarization patterns will help break some of the degeneracies that plague spectral and timing analyses, providing a more direct view of how the magnetic field is arranged. Coordinated multi-wavelength campaigns are especially valuable. An active magnetar can be monitored simultaneously in X-rays, gamma rays, radio, and sometimes optical or infrared. Each band responds differently to changes in the star. X-rays may show rapid spectral hardening and the emergence of new hotspots. Radio observations may detect the onset of pulsed emission or changes in pulse profile. Infrared measurements might reveal subtle brightenings as energy is redistributed. By aligning all these data sets in time, researchers can trace the sequence of events during and after an outburst. Does the spectral shape change before the spin-down rate increases? Or after do radio pulses only appear once the X-ray flux has dropped below some threshold? Or can they coexist with intense high-energy emission? Answering such questions requires careful timing and long-term observation, but it promises a more integrated view of magnetar behavior. Despite this wealth of observational techniques, many aspects of magnetars remain uncertain because the signals are faint, the events are unpredictable, and the systems are distant. Distances within the Milky Way can be estimated from associations with supernova remnants or from dispersion measures of radio pulses, but these methods carry uncertainties. The interstellar medium absorbs and scatters X-rays and optical light, complicating spectral analysis. Instruments saturate during the brightest flares, leading to gaps in the record right at the peak of the event. Some magnetars are hidden behind thick veils of gas and dust near the galactic center, where confusion with other sources is severe. As a result, the existing catalog of magnetars is likely incomplete, and the observed behavior may not capture the full diversity of the population. Future missions with more sensitive detectors, broader fields of view, and more capable polarimeters will expand the sample and sharpen the data. For now, every new outburst and every fresh detection add to a patchwork picture. Observations trace the outlines of how magnetars radiate and evolve, but the underlying physical processes must still be reconstructed through models. The instruments act as remote sensors, recording distant storms of light from stars the size of cities. And although their records grow steadily richer, they inevitably leave some questions open about what is truly happening at the source. Magnetars do not exist in isolation from their surroundings. They are born in the dense star-forming regions of galaxies and spend their lives embedded in interstellar gas dust and sometimes in the expanding remnants of the explosions that created them. Each magnetar occupies only a tiny volume of space, yet its formation and activity can influence regions far larger than itself. On the scale of a galaxy, the combined effects of many massive stars and their remnants shape the structure and evolution of the interstellar medium. Magnetars form as one outcome of massive star death, and their properties place them within this broader context. Observations show that most known magnetars lie close to the galactic plane in or near regions where massive stars are common. Some are still encircled by visible supernova remnants, shells of gas driven outward by the explosion that gave birth to the neutron star. Others are found in clusters of young stars or near molecular clouds rich in gas. These associations suggest that magnetars are young objects on astronomical timescales with ages typically measured in thousands to tens of thousands of years. Over such periods, their magnetic fields are still strong and their internal heat has not yet been lost. As a result, they remain bright in X-rays and capable of significant burst-in activity. Their presence in star-forming regions also implies that the extreme end of magnetic field strength is linked with the same galactic environments that host the formation of massive star supernovae and compact binaries. The energy released by magnetars contributes in several ways to the galactic ecosystem. The original supernova injects kinetic energy and heavy elements into the surrounding gas, helping to stir it and enrich it with the products of nuclear burning. Later, as the magnetar's magnetic field decays, bursts, and flares release high-energy photons and accelerated particles. These emissions can ionize gas heat dust and drive small-scale shocks in nearby material. Over the lifetime of a magnetar, the total energy released in this way is modest compared to that of the original explosion, but it is delivered in a different form intermittently in highly concentrated beams and flashes. In regions where gas is already marginally unstable to collapse, such injections of energy can either delay star formation by adding turbulence or conversely trigger new collapse by compressing material. The net effect may be subtle and difficult to measure, yet it is part of the web of feedback processes that regulate how galaxies convert gas into stars. Magnetars may also be connected to observed transient events beyond their own characteristic bursts. Some of the most luminous supernovae, known as superluminous supernovae, have light curves that can be explained if a newly born, rapidly rotating, highly magnetized neutron star deposits energy into the expanding ejecta as it spins down. In such models, the magnetar acts as a central engine spinning quickly in the first days to weeks after birth and radiating magnetic dipole energy into the surrounding gas. That energy is trapped and reprocessed into optical light, making the supernova brighter and longer lasting than it would be with radioactive decay alone. If this interpretation is correct for at least a subset of superluminous supernovae, then magnetars not only emerge from violent stellar deaths, but also significantly alter how those deaths appear to observers, creating events that stand out against the population of ordinary core collapse explosions. After the ejecta expand and become transparent, the central magnetar might remain as a more conventional, high-field neutron star or might evolve into a more typical magnetar. But direct observation of this later stage is challenging because of distance and faintness. Another arena where magnetars are invoked is the study of fast radio bursts, those millisecond duration flashes of radio waves from cosmological distances. Their short durations imply very compact sources, and their high brightness temperatures suggest coherent emission processes in strong magnetic fields. Magnetars offer a natural environment where such conditions occur. Models propose that sudden changes in the magnetosphere triggered by crustal fractures or by interactions with surrounding material can launch pulses of electromagnetic energy that generate coherent radio emission. The detection of a bright, fast radio burst-like event from a known magnetar in the Milky Way shows that, at least under some circumstances, magnetars can produce radio bursts similar in form to those seen from other galaxies. However, the diversity of fast radio burst behaviors complicates a simple one-to-one association. Some repeat frequently, others have not been seen to repeat. Some occur in environments rich in persistent radio emission, possibly indicating a surrounding nebula, while others seem to originate in more ordinary galactic regions. It is possible that magnetars account for only a subset of fast radio bursts, or that magnetars at different evolutionary stages produce different kinds of bursts. Alternatively, other compact objects might contribute. The current evidence is consistent with magnetars playing an important role, but it does not yet exclude other sources. On smaller scales, magnetars can shape their immediate surroundings through winds and outflows. A rotating magnetized neutron star can drive a particle wind, a flow of relativistic electrons and positrons that carries away rotational energy. In some systems, these winds inflate nebulae of synchrotron emission, as seen around young pulsars. For magnetars whose spin periods are generally longer and whose magnetic energy dominates such nebulae are rarer, but hints of extended emission exist around a few sources. In particular, following especially energetic bursts, transient nebulae may appear as the magnetar ejects plasma into the ambient medium. These structures, detected in X-rays or radio waves, can fade over time as the injected energy disperses. The dynamics of such nebulae provide another way to estimate how much energy was released in an event and how it interacts with the surroundings. In dense environments, shocks driven by magnetar outflows can accelerate cosmic rays, contributing to the population of high-energy particles that pervades the galaxy. The presence of magnetars also affects the demographics of compact objects as a whole. In regions with active star formation, the end states of massive stars include black holes, ordinary neutron stars, and magnetars. The relative numbers of these outcomes influence the rates of phenomena such as X-ray binaries, gamma-ray bursts, and gravitational wave sources. If magnetars preferentially arise from the most massive stars that still manage to form neutron stars instead of collapsing directly to black holes, then they trace a narrow band of progenitor masses. Their existence places constraints on the boundary between black hole formation and neutron star formation. Moreover, if many magnetars eventually evolve into less active high-field neutron stars that are indistinguishable from ordinary pulsars, except for subtle differences, they may be underrepresented in current catalogs. Population synthesis models that simulate the births and evolutions of neutron stars in a galaxy therefore must include magnetar channels to match the observed distributions of spin, magnetic field, and spatial location. Magnetars may even play a role in the environments of compact object mergers. In some scenarios, the merger of two neutron stars does not immediately collapse to a black hole, but instead produces a hypermassive or supramassive neutron star temporarily supported by differential rotation and thermal pressure. If this remnant possesses an extreme magnetic field, it can act as a powerful central engine for a short gamma-ray burst, and its afterglow driving jets and winds that interact with surrounding ejecta. The subsequent collapse to a black hole would end this phase. While such events lie beyond the typical lifespan of isolated magnetars, they share similar physics of strong fields and dense matter. Observations of short gamma-ray bursts and their associated kilonovae combined with gravitational wave data from mergers are beginning to test these ideas. In some cases, the afterglow light curves and late-time emission hint at prolonged central energy input, which could be explained by a magnetar-like remnant. Although magnetars represent an extreme, their existence helps frame the continuum of magnetic phenomena in astrophysics. At lower fields, ordinary pulsars accreting X-ray binaries and white dwarfs show behaviors that can often be understood by extending the same physical principles into gentler regimes. At higher fields, speculative objects such as ultramagnetized remnants in the early universe or in exotic compact systems stretch those principles toward their limits. By anchoring one end of the observable range, magnetars provide reference points against which these other systems can be calibrated. For instance, Laboratory experiments that study matter in strong magnetic fields and high densities cannot reach magnetar conditions, but they can explore trends that, when extrapolated cautiously, may be compared with magnetar observations. Despite these many connections, magnetars remain rare in observational data. Only a few dozen confirmed or candidate magnetars are currently cataloged in the Milky Way and nearby galaxies. This small number limits statistical studies and makes it difficult to draw firm conclusions about their role in galactic evolution. It also raises the question of how many magnetars exist but are hidden because they are too distant, too obscured by dust, or currently too quiet to attract attention. Old magnetars whose fields have decayed and whose temperatures have dropped may be nearly indistinguishable from other neutron stars, leaving only subtle traces of their past. Conversely, some transients detected in other wavelengths or in other galaxies may already be magnetar-powered events whose central objects are not yet directly visible. In this sense, magnetars occupy a dual status in the wider cosmic story. They are concrete, observable objects with measured positions, spin periods, and spectra directly influencing their surroundings through radiation and outflows. At the same time, they serve as proposed engines behind more distant or more luminous phenomena that cannot yet be linked to specific sources. Their confirmed behavior in the Milky Way provides a template that can be extended outward with appropriate caution to interpret enigmatic signals elsewhere in the universe. Yet at each extension, uncertainties accumulate. The exact birth conditions, evolution, and end states of magnetars are not fully known, so any model that relies on them inherits these unknowns. As observations improve, some of these speculative connections may be confirmed while others will be revised or replaced. For now, magnetars sit at a crossroads of ideas, tying together the life cycles of massive stars, the physics of dense matter and strong fields, and the transients that briefly light up the sky across cosmic distances. Magnetars, for all their intensity, are not permanent fixtures in their most extreme state. Like the massive stars that gave rise to them and the supernova remnants that surround some of them, they evolve over time. Their lives as ultra-strong magnets are thought to last for periods measured in tens of thousands to a few hundreds of thousands of years. A brief span compared to the age of a galaxy, but long enough to leave lasting imprints on their environments. As they age, their internal heat is gradually lost and their magnetic fields slowly decay. The details of this evolution are governed by processes inside the crust and core that are still actively studied. In the solid crust, electrical currents that support the magnetic field encounter finite resistance. Over long times, this ohmic dissipation converts magnetic energy into heat. The characteristic timescale depends on how conductive the crust is and on the geometry of the currents. In regions where nuclear pasta structures and impurities increase the resistance, decay can proceed more quickly, releasing heat that keeps the crust warmer than it would otherwise be. At the same time, the Hall drift, a process in which currents are rearranged by the magnetic field itself, can move energy between different spatial scales, concentrating fields in some regions and weakening them in others. Deeper in the core, where neutrons are superfluid and protons superconducting, the evolution of the magnetic field may be dominated by ambipolar diffusion, the slow motion of charged particles relative to neutral ones, under the combined influence of pressure gradients and Lorentz forces. This process is temperature dependent and becomes less effective as the star cools, coupling the thermal history of the magnetar to the fate of its field. The combined action of these mechanisms gradually changes both the strength and the configuration of the magnetic field. Early in a magnetar's life, the internal field may be highly tangled and strong, exerting large stresses on the crust and producing frequent outbursts as it tries to untwist. As energy is lost and the field simplifies, the rate of bursting may decline. Observationally, younger magnetars with estimated ages of only a few thousand years tend to be more active with higher persistent X-ray luminosities and more frequent bursts, while older objects appear quieter and cooler, though individual cases can deviate from this trend. Some neutron stars with inferred magnetic fields in the high range comparable to or slightly below classic magnetar values show sporadic magnetar-like activity, superimposed on otherwise ordinary pulsar behavior. These so-called high-field pulsars may represent transitional states, either neutron stars that never fully reached magnetar extremes or former magnetars whose fields have decayed. Their existence blurs the boundary between categories and supports the idea of a continuum of magnetic evolution rather than a strict division. As the external dipole field weakens, the rate at which the star spins down decreases. Over time, the rotation period lengthens until the magnetar no longer has enough rotational energy to produce bright emission via magnetospheric processes. The surface cools as magnetic heating diminishes and the X-ray luminosity drops. Eventually, the star may become difficult to detect except as a faint thermal source or as a weak radio pulsar if it emits radio waves at all. At that point, it would be hard to distinguish from other neutron stars based solely on current observations. Any record of its magnetar past would reside in subtle internal differences, such as residual composition gradients or remaining small-scale magnetic structures which are not directly observable. In some scenarios, especially for neutron stars born with masses close to the maximum that can be supported by their equation of state, the long-term evolution may include a delayed collapse to a black hole. If magnetic field decay or rotational energy loss reduces the support that helped hold up the star, the core could cross a stability threshold and collapse. Such late collapses would likely be rare and might produce transient signals of their own, but they have not yet been observed in a way that can be confidently tied to former magnetars. More commonly, the end state appears to be a slowly rotating, weakly emitting neutron star with a moderate field. Population models suggest that many such objects could exist in the galaxy, contributing to the unseen neutron star population inferred from supernova rates but not yet individually detected. The timescale on which a magnetar loses its distinctive characteristics is uncertain. Some theoretical models predict that most of the magnetic energy is dissipated within a few 100,000 years, while others allow for strong internal fields to persist much longer, buried beneath a quieter external dipole. Observational constraints come from the ages of associated supernova remnants, from the kinematics of magnetars moving through the galactic potential, and from the distribution of their spin periods and field strengths. These hints suggest that magnetars are on average young compared to the broader neutron star population, but the small sample size and selection biases leave room for multiple interpretations. Another aspect of magnetar fate concerns their role in cumulative feedback. Even after their brightest phases have ended, their earlier activity may continue to influence their surroundings. Regions of gas ionized and heated by past flares can take significant time to cool and recombine. Dust grains altered by intense X-rays may have had their surfaces sputtered or their chemistry changed. Nearby stars and planetary systems, if present, may have received bursts of high-energy radiation that affected their atmospheres or circumstellar environments. On larger scales, the integrated effect of many magnetars over galactic history could contribute in a small way to the overall ionization state of the interstellar medium. Separating this contribution from those of more common sources such as ordinary massive stars and accreting binaries is challenging. Yet the possibility remains that magnetars have left faint imprints in places where they are no longer present. From a theoretical perspective, the ultimate fate of magnetars feeds back into models of dense matter and field evolution. For example, if observations were to reveal a population of old neutron stars with unexpectedly high surface temperatures that could indicate long-lived magnetic heating, supporting models with slow decay of internal fields. Conversely, if old neutron stars are found to be consistently cold and faint, that would favor models where magnetic energy is dissipated more rapidly. Similarly, precise timing measurements of high-field pulsars and other candidate relic magnetars can show whether their spin-down rates match expectations from simple dipole breaking, or whether additional torques, perhaps from residual multipolar fields or fallback disks, are at work. Each piece of data constrains how the magnetic field and rotation evolve over time, and therefore how magnetars transition into other classes of objects. There is also the question of how many magnetars the galaxy has produced over its history. The current census includes only a few dozen, mostly young and active. Extrapolating from this small sample, correcting for detection biases and accounting for field decay, one can estimate how many dormant or relic magnetars may exist. Results range over wide intervals and depend strongly on assumptions about lifetimes and formation rates. But they generally suggest that there could be many more former magnetars than currently visible ones. These unseen remnants would contribute to the population of isolated neutron stars, and could occasionally be revealed when one experiences a late-time outburst or is discovered via precise radio timing as a high-field pulsar with unusual properties. In the broader scheme of stellar evolution, magnetars occupy only a small fraction of parameter space, yet they probe physical conditions far from the ordinary. Their eventual fading and transformation do not erase the fact that for a finite interval they host the strongest magnetic fields known, and that during that interval they act as engines for some of the most energetic transient phenomena. The arc of their evolution from birth in a core collapse explosion through an active magnetar phase to a quieter endpoint illustrates how small differences in initial mass rotation and magnetic field can lead to dramatically different stellar remnants. At each stage, they test theories of gravity, nuclear physics, and plasma behavior in regimes inaccessible on Earth. Even once they have cooled and dimmed, the knowledge gained from their earlier, brighter phases continues to inform models of other systems, from gamma-ray bursts to fast radio bursts and beyond. Yet key pieces of the story remain missing. The exact conditions that decide whether a neutron star becomes a magnetar are still not fully defined. The internal structure and composition that control field evolution and heat transport are imperfectly known. The long-term outcomes, whether quiet high-field pulsars, ordinary neutron stars, or rarer collapses, remain to be mapped with better statistics. Magnetars thus represent both a completed chapter in the life of some massive stars and an ongoing set of questions about how matter and fields behave under extremes. As observations and theory advance, more of their history will likely come into focus, but it is unlikely that the picture will become entirely simple. Instead, magnetars appear poised to remain as complex, evolving objects whose present appearance hints at a past that was even more extreme, and at futures that may diverge in ways not yet fully anticipated. Their fate, like their origin, is intertwined with a wider cosmic network of processes, and within that network, they continue to serve as signposts, marking the limits of what is currently known.